the intensity or the current squared. And so you always do have positive power, even though the current may be changing from positive to negative. Now with this expression, we can actually get what this, the functional equation of the power, because the power expression is the intensity squared, or not intensity, sorry, current squared times the resistance R. And if you actually carry out the squaring, you would get, and this is our term, then you would get I naught sine of omega t quantity squared times R, or this is going to be I naught squared sine squared of omega t times R. And so this will be the expression for power. Now, even though this provides to us the instantaneous power, at any point in time we can tell what the power is, this isn't very useful in terms of powering appliances. Because this happens very, very quickly. What the appliance really gets is, let's say, some average power. So this is P, we'll call this P average. And instead of writing for the average AVG, we'll denote an overbar that represents that's the average. So this is a notation. So we want to know what is the average power the appliance actually gets, even in alternating current. And direct current, it's very simple. But in alternating current, you see that it's continuously bobbing up and down, so we want to get the average value. So this is when we want to introduce what is called the root mean square. Root mean square. For the sake of saving time, I'll just give you the values. I won't do the derivation. The root mean square current is equal to the square root of 1/2 times I naught. And oh, I forgot to mention, this I naught here, that is just referring to the peak intensity. Peak intensity of the current. So I naught is the peak current. And so the root mean square value is the square root of 1/2 of your peak intensity. Likewise, the root mean square voltage is the square root of 1/2 of the peak voltage. So this is the peak current, peak voltage. Now if you plug the square root of 1/2 into your calculator, it's simply 0.707. So the root mean square values are simply 0.707 of the peak. And we define this root mean square because, recall, we had gone over an expression for power, which was IV or I squared R or V squared over R. Right, we went over these three variations for what power actually is. Well, if we have this root mean square value, then we can actually get the average power for alternating current. This isn't the vector, this is the average. This is actually going to equal I root mean square times V root mean square. Or an alternate form is I root mean square squared times R, or V root mean square squared R. So by defining the root mean square values, we can keep the algebraic form the same so that they are identical. So this is for alternating current. So defining the root mean squares allows us to just keep the algebraic form looking identical to the expressions that we've derived before. So let's do a simple example utilizing this. So let's say what was the question? Okay, what is the peak voltage What is a peak voltage for a US home? What is the peak voltage for a US home? Now, one of the things that we discussed for alternating current is that this is what power or electric companies actually provide to our outlets. It's alternating current. But what voltage in the direct current sense is actually coming out of our outlets? We went over this number? 120. Right, 120 volts. So the outlets are rated for 120 volts. But 120 volts, it's not coming as direct current. It's at what's actually being supplied is alternating current. So the 120 volts is actually VRMS. That is the VRMS that's actually coming out. Meaning, if you look here, so VRMS is that, but what we're looking for is V naught. So then V naught is equal to VRMS over 0.707 or 170 volts. So electric companies are actually generating 170 volts in terms of peak voltage in alternating current. And that's why when we use an outlet, we're getting 120 volts of usage. So, so essentially, the power plant is supplying 170 volts. Right, this is what it's supplying to us. Okay. All right, so this ends the electric portion. Now we move on to magnetism. Magnetism. This is
How would you say magnetism compares with electricity in terms of difficulty?
Oh, magnetism, I believe this is when the class gets hard, and we'll talk about, you'll see why in just a moment. This was probably the only section when I was an undergrad that I didn't fully grasp. Although I wasn't a good student, because I had such a high grade, I only needed a 40% on the final, and I knew that, so I didn't work on it. Oh, sorry, I needed a 50% on the final to get an A, so I didn't really study it. Guess what I got? I think you know the answer, I got a 40. So no, I didn't end up getting an A in the class. That was one of my few A minuses, unfortunately. Yeah, so this is actually a really hard material, but let's go over it, okay? So there's actually a lot of similarities between electricity and magnetism. One of which is the concept of a field. Well, we do need to cover a few different definitions before we get there. The first definition we have to go over is this idea of a pole. Idea of a pole. It is a location of strongest magnetic effect on a magnet. It's the location of the strongest magnetic effect on a magnet. This is not charge. And this is one of the reasons why it becomes extremely difficult. I definitely did give you guys words of caution to not think of charges as magnets, but I'm sure most of you guys kind of either ignored me or involuntarily started to think about it in that fashion. And that's one of the reasons why magnetism is going to become difficult. You think you understood it, but then I'm going to go over a lot of the differences, and then you're going to be like, wait, what? I thought it behaved in a different fashion, but no, that's charges. So you actually have a lot of unlearning to do, not because it was wrong, but because you thought magnets were, or charges were magnets. But right now we're going over magnetism, not charges. They are very, very closely related, and you'll see some of them soon. However, even when we're defining poles, one of the differences becomes very apparent. In charges, you can have a positive charge and you can have a negative charge. That's completely fine. In magnets, you always have a pair of poles. And we call them, so always have two poles. You always have two poles. They come in a pair. There's no such thing as just a north pole or just a south pole, and that's one thing that we're going to cover. In terms of magnetism, we call them north pole and south pole. And they always come as a pair. Whereas for charges, you can have an electron, which is simply negative, or a proton, which is simply positive. You can have mono charges, but there is no such thing as monopoles. Monopoles. Now, one of the similarities with or electricity is, in terms of magnets, we have the same thing. Opposites attract. Likes repel. So that definitely is one of the similarities, and this is where I think a lot of people are tempted to think of charges as magnets when we go over the electricity section. Another similarity is magnets generate magnetic field B. The magnetic field, we give the notation capital B. And so, like charges which generate an electric field, magnets generate a magnetic field. And like electric fields, we can visually represent the magnetic field. So like electric field with E field lines, we can draw the magnetic field with magnetic field lines. And so let's say we have a bar magnet here. We have north and south. Electric field points from positive to negative. Poles points from the north to the south. it points from the north to the south like this. So one of the things that you have to remember to distinguish is magnets from, or magnetic poles from charges. Now, unfortunately, the difficulty is just beginning. Like I said, part of the difficulty is you guys are likely understanding everything about electricity from the concept of magnets. So that's already a mistake, so you're going to have to override some information in your memory bank. Another difficulty is this question right here. Where does the magnetic field come from? Or actually, where do hold on. Yeah, we'll call it that, that's fine. We'll call it this. Where do magnetic fields come from? Any ideas? It is charges. And now the difficulty begins. I just got done lecturing you. Magnetic poles are not charges, they're not the same thing, but magnetic fields come from what? Charges, not magnetic poles. Now that's kind of crazy. Let me help paint the picture of how complex this relationship is by asking you a few questions. Let's test your instincts here. Okay, so charges generate a magnetic field. Okay, so let's look at an example. Let's say a current is flowing through a wire. And so this is our wire, the current is going in that direction. The question is, in which direction is a magnetic field? And let's make this multiple choice. Is it left, right, up, or down? Let's see a show of hands. So the current is going to the right, that way. Who thinks the resultant magnetic field would also be to the right? Raise your hand. All right, who says it'll be to the left? Raise your hand. Who says it'll be up? Raise your hand. Who says it'll be down? Raise your hand. Fortunately, the answer is none. It's a trick question. All right, maybe this was a trick question. Because the actual magnetic field is going in and out of the page like this. It's wrapping around the coil itself. Now here we see that even though magnetic poles and charges are not the same thing, charges and magnets seem to be related because charges actually give rise to the magnetic field. But this is not a one direction. Wait, it's not a one-way street. That's what I'm trying to say. It's not a one-way street because so charges lead to magnetic fields, but magnetic fields don't just work on poles, but magnetic fields also work on charges. So B effects B affects charges. So I'm telling you, poles and charges are not the same thing. So let's see exactly how different they are. In terms of poles, opposites attract, likes repel, that's really all you need to know. But what about for charges? And with that, let's ask another question. Let's say an electron is at rest in a uniform magnetic field B. And that uniform magnetic field is in this direction. And let's say here is our electron. And the question that we want to answer is in which direction will the electron move? So if the magnetic field is to the right, will the electron move this away, that away, up away, or down away? Let's see a show of hands. So remember, the magnetic field is pointing from the north to the south. Okay, so this is north to the south, north, south, north to the south. Then we put an electron in there. Who thinks the electron will move to the right? Raise your hand. Who thinks it will move left? Raise your hand. Who thinks it will move up? Raise your hand. Who thinks it will move down? Raise your hand. You can't answer it twice.
I think it'll move at an angle if I was going to give.
Oh, move at an angle?
Yeah.
Okay, so who says none of the above? Raise your hand. Okay, but then what's it? Alright, what guess do you have? Steve.
They just figured you out.
Well, if it's none of the above, you have to have an alternate answer, right?
I don't know, we'll just like move it at a coil, like the magnetic field.
Move in like a circle or something? What
Just a
about?
wild guess.
Mine's it doesn't move.
Actually, that's correct. The answer is none. It doesn't move. And you're probably like, Dr. Kim, you simply lied to us because you told me magnetic charge or magnetic fields affect charges. And this is true, and this is where things get very weird. Because as soon as I relax this condition, let's say the electron is no longer at rest, but an electron is moving, then the magnetic field will do something. It will change the trajectory. So, weird things are happening, and I understand. And the whole reason why I wanted this magnetism portion involved is for you to at least begin to think about it in preparation for the midterm, because obviously when we start to do, calculations and stuff, you're going to want to have a solid foundation. So some of this conceptual stuff will definitely be included on the exam. Now let's begin to at least dissect one of these, and we'll be dissecting the first of the two, and then we'll pretty much call it a day then. But one thing I really wanted you guys to see is there is a very weird relationship between electricity and magnetism. And guys, this relationship is extremely complex. These behaviors were known to be related for roughly 400 years. So for roughly 350 of those years, people understood it incorrectly. It's only in the past 50 years have we developed the more consistent model, and that's what we're going to go over. So scientists for 3.5 centuries got this wrong. So that's how complex it is. So let's begin to go over at least one of those. Right. And that is electric currents. And the magnetic field. So let's answer this question a little bit more precisely. Where do magnetic fields come from? Ultimately, moving charges or we could also say electric current they induce a magnetic field B. So moving charges generate a magnetic field. So it's not simply charges, it has to be moving. Stationary charges do not generate a magnetic field. Moving charges do. Moving charges do. And to understand the directionality of this is when we need, and we covered this in the first semester. Who remembers what this is called? Yeah, the right-hand rule. Meaning, let's say we have a wire going like this, and the current is going up. We're going to be using the right-hand rule, so everyone take out your hand. Which hand are you taking out? Okay, well, let's make sure we get that. Let's get that down. With your right hand, the thumb goes in the direction of the current. So in this example, our thumb is pointing up. And the curl of the fingers is your resultant magnetic field B. So with your thumb up, notice the fingers on this side are coming out. On the other side, it's going in. So the magnetic field is going to look like Saturn's rings. It's going to go around like this, and like this. And of course, it's not only up there, but it's at every single height. The magnetic field will look like this. So one of the weird relationships between electricity and magnetism is that moving charges generate a magnetic field, stationary charges do not. All right, why? Okay, you can ask God that when we get there, but that's how things work. So let's do a simple example with this. I want you to draw the magnetic field lines for a ring of current. And this ring of current, let's say we're going in and out of the page, so the ring from kind of like a three-dimensional point of view looks like this. And the current is going this direction. I need to draw it a little bit lower. So the current is going that direction. This is the front, and this is the back. So rings coming out, and then also going into the page. So we take out our right hand and we follow the direction of the current. So our thumb is going this way, and as we're coming out, the finger is going in, so the magnetic field will look like this. Above the ring, it's going counterclockwise. Oh yeah, it's going left to right to left, but inside the ring, it's going left to right. Currents like this. And so we're just going to follow that through, and then it's going to look this, this. This is the halfway point. At this point, it's just perfectly straight, and then it's going to be symmetric down. Except this is wrong. Actually, technically, no. Everything here is correct, it's just incomplete. Because we only drew this for directly down the middle of the ring. Now, due to the nature of having to use the right-hand rule, we do need the full 3 dimensions. Now, let me remind you guys of some of the notation that we discussed before. Recall, we use a dot or a circled dot for out of page. Do you guys remember this? Or we use an X or X circled for into page. The reason why I'm saying this is incomplete was, okay, I was actually gonna, well, this is part of the problem set, but I'll just give you the answer here because the midterm's tomorrow. And I'll just do one of those problem set for you guys. For that ring, let's draw the 2-dimensional way, and let's say the current is going in this direction. Current's going this direction. So the problem set problem was, instead of doing this, use the dot and X notation to actually draw correctly the magnetic field lines for this scenario. The reason why I'm saying this is incomplete was all we did was draw the lines for right along this line. We only drew what these lines were for as it lies on this plane. However, we don't give any sort of answer for anything to the left, to the right, whether it's outside or the inside. So instead, we need to adopt this 3-dimensional rule, so let's do it self-consistently. If the current's going this way, you take out a right hand. When it's outside of the ring, notice my fingers are going, is it into the page or out of the page? Right, it's into the page, so everything out here would be an X. And you'll get this if you just follow your entire arm around. So you're always pointing into the page when you're on the outside. But what about inside the ring? You see your fingers are now coming out. So inside, it's going out of the page towards you. And this is up to the point where I expect you guys to know magnetism. And I don't think it's fair for me to continue going, so we will end lecture here. Oh, except Kylie had a question.
Oh, it was how to solve for the I values from the other night.
Yeah, if you want to stay for that, you can. Otherwise, the lecture has concluded. So Kylie, can you give me the the equations?
Yeah, it's I1 plus I2 plus I3. The second one was 125 minus 21 I2 minus 41 I3 is equal to 0. And then 45 minus 30 I1 minus 44.
That doesn't sound right.
No, it must be 41. Yeah, 41 I3 equals 0.
Are you sure this was 30? It wasn't 31? It's 30? It was 30? Okay. So how I would solve for this, essentially, I would substitute first I3 for I1 plus I2. So I see both of these. I see I3 here and here. So I'll plug in I1 plus I2 here and here. So let's first do it for this one. 125 minus 21 I2 minus 41 times I1 plus I2. That is equal to 0. We can distribute the 41, so we get 125 minus 21 I2 minus 41 I1 plus 41 I2 is equal to 0. 21 I2, 41 I2, or sorry, negative 21 I2 plus 41 I2. Those are like terms, so we can cancel those out, or at least do the arithmetic. What wins out is plus 20 I2 minus 41 I1. That is going to equal 0. So that's what the second equation turned into. We now need to make the substitution again for equation number 3. So we have 45 minus 30 I1 minus 41 I3 is the I1 plus I2. And so we distribute the 41, so we get 45 minus 30 I1 minus 41 I1. Wow, I completely made a mistake. It's the negative 41 that gets distributed. This is actually negative. And so it's minus 21 minus 41, so this should be minus 62. Sorry, I made a mistake. Likewise, this negative 41 gets distributed to both, so it's minus 41 I1 minus 41 I2, that is equal to 0. Here we see the I1s share the same variable, so it's minus 71 I1 minus 41 I2 is equal to 0. From here, I could solve for I1 on either one of these equations and then plug it into the other. Let's do this one. From here, I want I1 is equal to blank. So we begin by isolating. So we're going to get 41 I1 is equal to 125 minus 62 I2. All I did was add 41 I1 to both sides. And then I would divide everything by 41, so you get I1 is equal to 125 over 41 minus 62 over 41 I2. This, you would plug into this I1 here. So this becomes 45 minus 71 times this entire thing, 125 over 41 minus 62 over 41 I2 minus 41 I2 is equal to 0. So we can factor out the negative 71, so this comes out to be 45 minus, we'll just write it like this, 71 times 125 over 41, plus 71 times 62 over 41, I2, minus 41 I2 is equal to 0. Here, what is the only variable we have? I2, both of these share it, so let's actually factor it out. So instead of writing it like this, we'll do that. So 71 times 62 over 41 minus 41 I2, so this means I2 is equal to 71 times 125 over 41 minus 45. All of that divided by 71 times 62 over 41 minus 41. And you guys have a calculator, you guys can plug that in and that just gives you a number. So we'll say I2 is equal to, I don't know, whatever this is. This I2, then we can simply plug into here, so I1 is equal to 125 over 41 minus 62 over 41 times whatever that is, right? This is just a number. This is just a number. Now I1 is also a number because it's a fraction minus another fraction, and we'll call it whatever this is, but sideways. From here, we can plug it back into here. I3 is I1, which is whatever this was, plus I2 plus whatever this is. Right, you guys have calculators, you guys can plug that.